Hello, thanks for joining us for the AIR Distinguished Speaker Series. We're very lucky to have Charlie Wang here joining us today. So Charlie is a professor of smart manufacturing at the University of Manchester in the UK. And Charlie and I have been collaborating for many years, probably around a decade, possibly more.
I think more than that.
Maybe even more than that. So I have many good experiences working with Charlie and a big fan of his work, so it's really excellent to have him here at Boston University. He's received many awards, so he has been given the American Society of Mechanical Engineers CIE Excellence in Research Award, the Young Engineer Award. He's a fellow of the American Society of Mechanical Engineers. He's also received 9 Best Paper Awards, so very decorated. And previously to being at University of Manchester, he was also at Delft University of Technology as professor and chair of advanced manufacturing, and also at the Chinese University of Hong Kong. So we're very glad to have you here. Thank you, Charlie.
Okay, thanks, Emily, for a nice introduction. It's my great honor to be invited here to give the district seminar. So today I'm going to talking about some of our recent research about field-based computation for vector 3D printing with a focus on slicing specifically. And of course, I will extend a little bit to the Toolpath generation and motion planning, okay? So, well, I do 3D printing for many years. So every time when I start to introduce people about 3D printing, it's like things about 10 years ago, it's a bit embarrassed. So it's basically because 3D printing is not really doing 3D printing at the moment. So most of the case, I would like to call it 2.5D at this moment. So this is because think about the way how the materials really accumulated in the conventional 3D printer, what you see from day to day. It's pretty much layer-based, especially planar layer-based 3D printing technology. And of course, when it's invented, this brings in many of those very nice parts of the process, especially for engineers who are not very familiar with computer science. You simplify the algorithm. So it's basically using planar layers to really cut the 3D geometry. And you have many of those simplified way to really process material. But this actually caused a lot of problem to us. Okay? Think about one of the problems. It's like the first paper I collaborated with Emily is about how to handle those supporting structures. So think about many of those, the dragon models, it's like you generate many of those supporting structures below those large overhang. So it turns out those supporting structures cause many problems, including like hard to remove, surface damage, and also waste of material for sure. That's not the focus of today. I hope it worked. So I'm more focused on like the mechanical part of it. So think about what I show on the left of the screen. You have a lattice structure, which is widely used for those lightweight design in mechanical engineering. So you have many of those bars. So if the bars are sliced by 2D planars, it generates a lot of very small fragments which is stitched together, which has caused a very weak mechanical property. But if you don't accumulate material in that way, instead of using those planar layers, you extract those material directly along the axial direction. That's giving you much better mechanical property. So what is shown on this picture is like a slightly curved layer. And then we're using planar layers, so it turns out you have very bad adhesion between those planar layers. And when you apply it for 3-point bending, it easily generates damage, which is basically delamination. Okay? So, but if you slightly really printed a slightly curve along those axial direction, which gives a much stronger property. Mechanical-wise, this is easy to be realized by the multiple axis motion stage and the robotic arm. But software part, it still have a lot of problems. So our journey starts from this SIGGRAPH paper, which is published 2018. We're trying to using a fixed printer head and trying to rotate those underprinted object below it. So it turns out we're able to fabricate all those models, what is shown on this screen, in a support-free way. Okay. But besides of that, let's looking at the simple mechanical part of those 3D printing. The simple tensile bar was what I show on the left of the screen. if you print it along different direction and you apply it for the tensile testing, so you will find like they have a totally different failure points along these three different directions. One of the major reasons of that is because if you're looking at the microstructure of what you are 3D printed by using filament alignment, you generally find like there are many of those uncontrolled pulse, which happens between those layers and between those filaments. That's, of course, a very strong anisotropic mechanical property during your printing process. So we call it a vector 3D printing because we are trying to really align filament along the direction it should be and give you the strongest mechanical property in the space instead of on the planar layer. So our first piece of work, which is along this direction, happens in 2020, which paper we published in SIGGRAPH Asia. And then at that moment, we're trying to align those filaments really along the direction of maximum principal stress directions. And then what is shown on the left is like if you have a 3D model which is under certain loading, you pretty much have the tensor field which we can generate it inside of the model. And then with those tensor field, we are able to extract those maximum stress direction. So ideally, you need to generate a curved layer which is following this maximum stress direction. So it turns out to make it easy to generate like filament along those maximum stress direction. Okay, so we apply the basic idea of what we did here is like we're applying a two-level of decomposition process. The first process is like we're trying to decompose those volume into surface layers. So we need to generate those layers which is nearly parallel to those local maximum principal stress directions. Okay. And then after those decomposition, we have those surface layer, what's shown on the right. And then we're trying to align those two paths, which pretty much follow those principal maximum stress direction. Okay, so this is the basic idea. And let's see how we realize it. So basically, if you're directly calculating the vector field inside, that's caused a lot of problems to generate highly nonlinear objective functions, which is hard to converge during the numerical computation and blah, blah. So we are trying to decompose the whole thing into two levels of optimization. So first of all, we are trying to generate a set of, let's say, the vector field, which is kind of orthogonal to the direction which you wish to generate. Okay, so it's pretty much think about the objective function, the objectives which we are trying to optimize is trying to let those filaments pretty much following the maximum stress direction. And that means what? We need to have those surface layer embedding those directions inside. And then the normal of that surface actually gives you the direction which is following the minimum stress direction, right? So minimum, maximum, and the middle, they are orthogonal to each other. So our first decomposition is trying to generate those vector field, which is pretty much following the minimum stress direction. At the same time, those vector field need to be compatible with each other in the nearby region. And after that, we're trying to convert those vector field all the way back into a scalar field to let the scalar field's normal direction align with those vector field. So that is the solution we realized at that moment. So with the help of that, we're able to really compute everything on volumetric mesh. So it turns out we have a continuous representation inside of whole domain, although it's a piecewise linear representation. But that's caused a lot of, give us a lot of benefit. So it turns out, as what you can see from those bunny model, you find like those layers, which pretty much give you very nice boundary following the original model. And then those curved layer generated inside naturally fit with the surface boundary. Okay, so this is very good for the downstream design manufacturing process. And then after we generate those curved layers, so we pretty much is able to really project those stress field onto those curved layer. So we apply the same principle on this surface layer again. So basically, we generate another vector field which is orthogonal to those maximum stress field. And then using that vector field, you give in the normal of the scalar field. And then we have those scalar field, which is give you the iso curves of those scalar field give you the two paths. Okay? And then combine these two paths with those boundary two paths. So pretty much if you want to have very nice surface quality. You wish to have those two paths which is aligned or generated on the boundary following the boundary. So we're using the boundary distance field and then mix them together, and then we're able to generate the final two paths. Okay. So, and then what is the supporting structures? How are we able to generate that? So our method is pretty much based on the field-based computation. So when you have those scalar field naturally computing or optimized inside of the given model's domain, you're able to easily extend it to the outside. So we are generating a kind of a bounded volume outside of the original model, which is define the volume where you should put in those supporting structures. And then you apply the field explanation onto those regions, and then you are able to have a very dense supporting structure, which is able to be generated for multiple axis 3D printing. And then to simplify that, or to reduce those material usage, you're able to generate those kind of convolution surface-based tree structures inside of it. Using the implicit solid representation, you're able to have those lightweight supporting structures, which is able to realize as an extension of those field-based computation for optimization. Okay? So the idea is quite simple, but if you're looking at those results, so we're able to realize everything of this on our multiple axis 3D printer, which is something we modified from, let's say, our multiple axis CNC machine, this milling machine, but we removed those two by replacing it by a 3D printer head. So we are able to 3D print models like this. This is real-time printing process. It's actually quite slow, and then because you can't move in too fast, the material accumulation takes time. So after we fabricate this model, let's look at the results. So this is show the comparison. The left-hand one is actually purely planar layer-based 3D printing. Okay, the same material, the same amount of material, the same weight. The only thing we change is like how you align with those, how you align those material inside of this whole solid. And then we find that like the breaking force is almost a double on the right. This is basically because you're really using the material in a way that they're following the maximum stress direction, which is maximize the usage of the material, okay? And then so this gives us a very good confidence, so we are able to really using those multiple axis 3D printings give you a very nice material assignment inside of the domain. So we are trying to play this together with many other objectives. So at the same time, there's in parallel, many of those research happens in graphics community and also some other community like manufacturing and also construction, okay? So some of those research are trying to really reduce supporting structures. So we are able to fabricate it in a support-free way. Some of them really care about surface quality. So if you're looking at 3D printing, so one of the major problem of surface quality is like if you have slightly, have some of slope which is slightly tilted, and you have many of those staircase effect, which is easily to be observed on the surface. So it turns out people are trying to align those final layers, either is completely following with those coverage surface, or you're trying to make it completely perpendicular to those surface, which you are trying to produce. And then not mention about those maximum stress direction and so on and so forth, okay? So in 2022, we are trying to find a way to really combine these multiple things together. When we think about combining things, the first direct consideration is like, oh, of course, we define multiple objective functions, we're using way to blend them together. But definitely, if you do in this way, the final result is like you optimize nothing. Okay, so you can't control the balance between all those things. So what we are trying to do is like we're trying to find out a way that we're able to define those local printing direction inside of every element. It's like every local region. We're trying to define all those local printing directions which are compatible with each other. And then I think about what is the requirement of those local printing direction if we are trying to somehow satisfy certain requirements. The first thing, support-free. So it's basically you have the surface normal. You're trying to really tilting those printing direction to make it satisfy certain angle between the printing direction and the surface normal. So that gives you some requirement, right? So if you printing direction does not satisfy with that, so you basically are trying to rotate those printing direction. So which is a rotation-driven kind of local, say, a change or local adjustment you are trying to achieve. And then the printing direction the same, because basically you are trying to print in the direction which is along the maximum stress direction. And also surface quality. So all of this can be formulated in a way that satisfies certain requirement of a local rotation. So if you have all those local rotation requirements putting together, so we are trying to formulate this problem as a parameterization problem. So basically we're trying to deform the original model into another domain. So it turns out the height field in the other domain can map the back to give you the scalar field. Okay, that is the idea. But the thing is, like, if you think about multiple material, I mean the multiple requirements, are they really compatible with each other? Which is very important to conduct the following analysis, which is why we call it compatibility analysis. So each of those requirements actually define a kind of a half space in the Gaussian sphere, which gives you a definition about what is the feasible region. And that means what is the region that you are trying to rotate your z-axis into that region, which gives you the satisfied requirement. So for support free, you have some of the local region defined like this. For surface reinforcement, you have another half space. And then for surface quality, you have the third half space. So our analysis shows, at least locally, all these three half space, they have common region. That means every local region, at least you have one solution which is able to satisfy, or multiple actually. So all those red regions are possible solutions to making all these three requirements satisfied. Of course, when you're blending all those local requirements together globally, you may still does not have a global solution, but at least locally we prove that this solution does exist for those local regions satisfying multiple requirements, which is very important. And then we apply to, say, trying to find out what is the best local rotation. So we're using quaternion field, which is a vector representation of rotation, which satisfy all those requirements as putting at the hard constraint, as what is shown here. I hope you can see the mouse, okay? And then, of course, those quaternion field locally, they need to be compatible with each other, okay? This is sort of the local, the internal loop. So basically you compute a best local quaternion field, and then the external loop, we still need to blending all those quaternion field driven kind of a rotation together. But that can be easily realized by extension of about as rigid as possible deformation. So we don't really control its rigidity. Instead of that, we allow certain level of a scalar field or scalar kind of a change. So with the help of that, we're able to really compute a very nice deformation. So basically, this is the best deformation we can achieve according to all those three requirements: surface reinforcement, mechanical strength reinforcement, surface quality, and also a support-free requirement, which is satisfied on this model. So what you can see here, this gives you the curved layer, right? Which is completely follow the principal stress direction. Okay. And then so we tested on the very famous armadillo model. So as we try support-free mechanical strength and also surface quality. So as you can see, the surface quality is really satisfied by, say, the large layer, the final layer completely following the surface, and then some other layers from this side you can find as boundary of the layers nearly perpendicular to the surface. So either completely follow or perpendicular to that is satisfy all those requirements. Okay, and the scanning result also demonstrates like the surface quality of curved layers definitely much better compared to those planar layer-based results. Okay, so, but we don't stop there. So if you're looking at the real major problem of all those previously introduced methods, like all those methods, we heavily rely on a very, the volume mesh with very good quality. So for those of you conduct simulation, you probably find like it's extremely hard to really find a very good quality. I mean, the mesh with a good quality, right? So not talking about, if you're looking at some models shown like this, of course we make it on purpose, but it does exist. Some of the model in reality happen like this. So basically you have a model which is simply putting them together. The designers say, oh, we have a solid here, and then this is just a simple thin shell model. And then the other part is like a skeleton model, which is maybe have solid skeleton and also have tubular skeleton, okay? So how are we able to find out a good solution to give you the printing toolpath, which is satisfy all those requirements, at the same time being able to 3D print a model like this? So this is one challenge we're facing when we are starting to working on those neural slicer solution, okay? And then the second thing is the multiple objective optimization approach, which is we define it by the reparameterization. It sounds great, but the thing is like the requirement of support free, what we define is actually defined inside of those deformed domain. And then when we evaluate everything in the deformed domain, after we deform it back, the original satisfied requirement may not be satisfied anymore, because there's always certain level of distortion between the deformed domain and the original domain. So the thing is like, we wish we were able to directly evaluate everything in the original domain instead of the deformed domain. Right? So this is the second problem we're facing. And the third problem, of course, all those numerical optimizations heavily depends on good initial gas. As what we show on this yoga model, it's like if you give in different initial gas, they definitely give you totally different kind of curved layers. And then so last year, we proposed a new method, what we call the neural slicer. We're trying to tackle all those things together by using a neural implicit-based representation together with a volume mesh, which works as a cage. Okay? So the idea is very simple. It's like you first of all generate a cage mesh. It does not need to be a mesh completely follow the original mesh. As long as you have the cage mesh which is able to contain everything inside, which is good enough, because we're going to using this cage mesh to serve as an intermediate representation to help us generate the deformation. Okay? And so it turns out we're able to also convert every of the original model back into a solid representation. As long as it's a function, as long as it's an implicit representation, we're able to conduct the slicing, that which will be very helpful. And then finite element analysis can be also taken by the other representation. So basically, we're using the voxel-based representation to calculating the finite element analysis, which is actually a de facto standard of topology optimization. Many people using voxel mesh for FEA. So with the help of that, so we're able to generate FEA inside of a voxel set, which is a scattered representation or sample-based representation of tensor field, right? And then, but at least we have some of those samples which is able to obtain. So start from that. This is a pre-process. So we have implicit solid, which is embedded inside the volume cage. So our idea is like to convert the quaternion field and the scaling field, which we conducted in the S-cubic slicer, as a neural network representation. So with the help of this, we're able to using a meshless representation for neural field-based representation to deform the original cage mesh into a new cage mesh. Okay? So the best part of that is like after this deformation, we're able to directly map everything back into the original domain by using those scalar fields as a height. And then so we're able to evaluate everything like a local printing direction inside of the original domain. Okay? This gives us a lot of now we don't call it objective function because we're following the terminology of a neural field-based computation. We define the loss. So all those loss actually according to the thing we defined previously under like surface quality requirements, support-free requirement, and so on and so forth. And then with the help of this loss function, we're able to apply the back propagation, propagate everything back to update those neural network. The coefficients of the neural network actually now becomes the design variables of us. Okay? So this shows the iteration process, which is actually generate all those layers during those iterations, which is satisfy all those loss functions, which is defined according to manufacturing requirements. That's pretty good. And then we're able to conduct everything in the cage instead of on the original mesh. But the good thing is that is like our original models already converted back into a solid-based representation. So with the help of that, we're able to really generate those layers inside of the cage and using the implicit solid to conduct a Boolean operation to have the clean boundary of those layers. So it turns out you have all those things which is able to realize by this neural-based representation. So this shows the layers, what we generated by this neural field-based optimization. You can find like completely follow all those requirements we put in there for the surface quality and also overcome the problem of mesh representation and everything directly evaluated inside of the original domain. So this is the best part of this representation. And then surprisingly, we find like, if you're looking at the right one, the bridge one, and this is the result of S-cubic slicer, which sounds very smart, but turns out the neural network-based solver gives us a much better solution. So the whole bridge, if you rotate it a bit, and that's actually shown on the right, and then nearly planar layer actually gives the best solution, which is much better than our originally calculating result by the nonlinear optimization. This is because this one does not give you a good initial guess, but think about what is the nature of Adam, which is the numerical solver we're using for neural network-based training, which is stochastic gradient solver, right? So it's giving you a lot of random guess as an initial guess. So it turns out to converge very faster to this much smarter solution, okay? And not talking about those topology optimization results, which have a high genus number. So all those models are something which is hardly to be managed by the earlier curved slicer-based solutions, okay? And then we also change our hardware. So it's kind of, we upgrade our hardware system a little bit. So now we're using like 8 degree of freedom solution, which is using one, say, strong 6 degree of freedom robot arm working together with a 2 degree of freedom tilting table. And then so it turns out we have a much better printing quality. I will come back to this a little bit later, why we need to have this high degree of freedom, okay? So as what you can see here, all those models can be completely printed by using this advanced model without support for some of the regions, some of the examples. But for this model, which is far more challenging, so it turns out we still need to have a certain level of supporting structures, okay? So the key message I'm going to deliver today in the first part of my talk is like the multiple axis 3D printing is actually giving you a very good tool. We're able to change many, many downstream applications. So I call it a kernel. This is because with the help of this field-based computation, you are able to change all the way from part repair, printing electronics, large-scale construction. And then this is a very interesting research. Is like we're trying to print those optical lens in a very small scale, but turns out the surface quality plays a very important role in those optical lens. So you need to have very smart solution, and not talking about like we are applying those multiple axis 3D printing into those tissue engineering to print alive the tissue with the blood supplied at the same time, something like that. And then we target on one major application. This is like my major collaborators from the aerospace engineering and also vehicle engineering about like composite fabrication with the help of continuous carbon fiber, okay? So what is that? So basically, if you think about the way how we are aligned with the material inside of those, the whole domain, we're still using the conventional thermoplastic material, right? So we are trying to extend it to continuous carbon fiber. So with the help of that, as what you can see here, in this are like continuity reinforced Toolpath generation. We're able to generate pretty much continuous fiber or toolpath inside of whole domain, but the formula itself is still quite similar to what we did before. But the only thing is like we need to enhance the continuity of the toolpath. So it turns out you have continuous carbon fibers which is go inside of the solid. Simply say serve as a tendon of inside of the muscle, something like that, right? So here shows some of the example we conducted last year. So we are 3D print like model like this, which is a topology optimization result. And then this shows a comparison between the planar layer-based printing result with those really curved layer-based 3D printing result. As well as you can see here, those black curves actually show the continuous carbon fiber, which is distributed inside of the whole domain. And then think about the breaking force, what we can achieve before we're using continuous carbon fibers 2 times, right? Still remember the first example I shown today is like the planar layer-based printing and the curved layer-based printing, the breaking force is doubled. But think about this. And then this is like, with the help of a continuous carbon fiber, we are able to maximize those breaking force by 5 times. So, which is actually change many, many things. So basically you can use in less material, you can make it super strong with the help of continuous carbon fiber inside of it. That generates a lot of impact at the end. Okay, so Airbus start to collaborate with us on these topics, and then we find out like, this shows a very interesting result. Is like if you go for those microstructures, I mean you go inside and then to really find out those structures inside of those breaking region, and you find like if you're using the planar layer-based printing process, so basically after the structure is broken, the continuous carbon fiber is still complete inside. The only thing happens is like the delamination between the continuous fiber and the matrix material, okay? But if you're looking at the curved layer-based 3D printing, you find like the fibers are broken. So it's basically that's maximize the usage of fiber inside of those 3D solid, which is very important. That's why we're able to achieve up to 5 times of those breaking force. Okay. Sounds look like this is very great results, and also we demonstrated on many other examples, which is all super good. But when we start to discuss with our collaborator of a National Composite Center, they say, yes, Charlie, this is a very nice result, but we care about the other factors as well. What is the volume ratio of your continuous carbon fiber used inside of solid? So think about the toolpaths what we have. So you find like they are quite sparse, right? So it's basically this is because we don't have very good control about those distance between those neighboring toolpaths. But if you're really trying to reinforce that during the optimization result, you're not able to get in very good optimization convergency. Okay, so how we are trying to tackle this issue? This also shows another example. It's very quite sparse kind of continuous carbon fiber already maximize its usage, but the density of it is not good. So this motivates us to really conduct the following research, which I shown here today. It's like this year we generate another method. We're trying to really enhance the continuous carbon fiber toolpath generation inside of whole domain. So it turns out we are able to achieve very dense continuous carbon fiber toolpath inside of that. Okay, so I think this research is also inspired by our private communication together with our group and also Edward here. So I think we meet each other during the conference. We discuss about those kind of spinning form about things. So my PhD student go back say, oh, Professor Edward Chen, you give us a very good idea to use in spinning form, and then maybe we can try this. So we come back to work out this solution. So think about the way why we are not able to generate very dense toolpaths. One of the main reasons is like we're using vector field, of course. And then vector field basically comes from those tensor field. But if you doing the eigenvalue decomposition or eigenvector decomposition, you don't have a consistent of those orientations. So you need to somehow always find a balance between them. And then the vector field itself does not really solving the problem. And the other issue is like we're using scalar field to generate toolpaths. So these are the two major issues. We cause the sparsity of those toolpaths. So, and then we're trying to tackle it by different change of our primary scheme. So first of all, we convert vector field into two Rossi representation. So that gives you a direction independent representation, right? So, and then we change the scalar field into a spinning form with the help of periodical parameterization. So we're able to generate a very dense kind of wave-based field. So it turns out with this wave-based scalar field or periodical scalar field, we're able to generate very dense toolpath. Okay, so this is a trick, but this trick helps us a lot. If you're looking at the solution we've shown here, this is toolpath. I mean, this is still the pipeline, but that definitely gives us a very good and very dense toolpaths, which help us to significantly enhance the density of toolpaths. So this is very complicated model. As what you can see here is highly curved surface, but we're still able to decompose a very dense continuous carbon fiber on top of that, and then shows the comparison. So basically the original method, the carbon coverage ratio is only about 26%, and with the help of spinning form and two Rossi representation, we can all the way increase it to 88% of the coverage. Okay, that just shows a big difference. If you're looking at those mechanical property tests, and you find like diffraction force increased by 80% as well. Okay, so this shows, from this image you can see like the original kind of scheme, the density of a continuous carbon fiber inside is quite sparse. But with the help of spinning form, we are able to generate very dense kind of continuous carbon fiber inside. Okay. And so, in conclusion, today I covered multiple axis 3D printing, which is able to help you align with the mechanical anisotropic mechanical property inside of the field very well. So we're using field-based computation and slicing and toolpath generation, all based on field representation. But there's still one further step we need to think about is like how we really realize those continuous toolpaths we generate inside. So we still need to realize it on the machine. So we still need to cover those things about trajectory planning and also those machining-based optimization on the machine itself. So one of the major issues, as what we seeing here, is a called singularity. So what is the real singularity making by the machine itself? If you look at how the machine works, you're trying to print everything inside of the model's domain in an arbitrary direction. But when we map it into the hardware cannot realize that. So what the hardware realizes that is like the rotation happened by those tilting table. Okay? So singular region is actually when you have some of the local orientation inside of the model domain slightly away from the z-axis. Okay? Just slightly away from the z-axis. But how this is realized on the hardware of the machine is like you need to have this plate, which is called c-axis, rotated a little bit, right? Very fastly. So it turns out you have slightly tilted orientation. You need to have a superpower motor, which allow you have the c-axis rotate very fast, which is hard to be realized. So this is called machine singularity inside of the domain. So we need to try to avoid that. So one of our research is like we're trying to optimize the orientation and the toolpath. So we're able to reduce all those large rotation of c-axis. Okay? So you say, why you trying to do that? Because you can have a superpower motor, but actually that's not. We are not able to have a superpower motor. And then the problem is like when your rotation is not fast enough, don't forget you are really working with two machines. One machine is this moving stage. The other machine is the extruder. Okay, the material extruder. And then material extruder does not really well synchronized with this rotation. So it turns out the insufficient rotation caused the problem as what I can show here on the this image. So I want to stop here a little bit, maybe back a bit. So you can see like the left picture actually showing the insufficient material extrusion. This is mainly caused by the insufficient rotation on the z-axis. Okay, and then with the help of optimization, you have a better quality control about printing. This is not about surface quality. It's more about mechanical strength, because on the left one, you generate many of those porous structures, which has caused a lot of problem of mechanical strength. Okay, on the right, with the best of those control, you're able to have much better results. So this shows also on the other really 3D model, so I can show here, on this setup, as well. So you can see with the non-optimized result, you have many of those artifacts which is caused by the singularity of those motion. On the right one, after we optimize it, you have more continuous like toolpaths which can be realized on the machine. And not talking about when we're moving from the 5-axis motion into the 8 degree of freedom machine, so we have more degree of freedom to really play with. So we have a much better kind of machine coordinate system, which give you kinematics redundancy and give you the flexibility to really optimize many of those possible solutions. Simply saying that one position, one orientation, now you have much more possible or feasible solution which you are able to realize on the machine, and then that gives you the benefit of those motion planning. So it turns out you're able to optimize not only to avoid the singularity, but also you're able to optimize the continuity of velocity, acceleration, and the derivative of acceleration, which is called a jerk. Okay, because during the printing process, it's generally much vibration if you have a large jump of jerk, okay, which is very important for the continuous machining aspect. And then so one of my PhD students realized this software solution. So you can see like without optimization, you can see many of those shaking which happens on the non-optimized result. But with the help of optimization, you have less shaking about z-axis and also have a much continuous material accumulation happens inside of the domain. I'm going to finish soon, all right? So, and then this is realized on this hardware which have more degree of freedom. And then this shows the variation of those derivative of acceleration before optimization and after optimization, and so on and so forth. And then, yeah, this shows the quality. You can see like usually those local shaking of acceleration cause many of the problems of material accumulation on the surface quality and also the mechanical strength. Okay, so this shows another result. And also we realize on different configurations of the robotic arm. Okay, so in summary, we are trying to tackle the whole problem of 3D printing, vector field-based 3D printing, many of those 3 different aspects, including slicing, two-pass generation, and also trajectory planning or motion planning. But still, many of the challenges exist. So it turns out my research group are taking the following project in parallel right now. One of the major things is, it's a bit another embarrassed part of 3D printing communities, like all the 3D printing right now is pretty much open loop. Okay, so you don't have feedback, so you don't have a quality control of the printing process. So we are trying to using force-based sensors, trying to control the quality of 3D printing. So it turns out we're able to adaptively control or adaptively change the planner and the toolpath, many of the things. And also we need a newer design of a printer head for continuous carbon fiber fabrication right now. So it's still quite a challenging issue. Not talking about so far all the things what we've done and what I've shown here, we don't change the design of the model. But many of those cases, we find like if you don't allow to change the design, it's hard to really realize all those manufacturing objectives. So the better solution is like integrate design and manufacturing together in an integrated optimization, so it turns out we're able to realize the real optimized solution for design manufacturing. Okay, we hope some of the new research outcome will be able to publish soon along all this line. And at the end of my talk, I would like to thank my team. So you can see Jessie is also there. This photo is really taken during her visit to us in Manchester. And then this is actually a picture we taken before we joined the TCT annual additive manufacturing exhibition. And I really appreciate I have a strong team who is able to work closely with me working on those things. And also my collaborators all the way from INRIA, TUDELF, CUHK, Emily as well. And also Tsinghua University and my funding agencies, industry collaborators, and so on and so forth. Okay, I think that's the end of my talk. I'd like to answer your questions.
Inspiring talk. So we have some time for questions from the audience. Yeah, thanks for the great talk. I noticed that because you're printing different layers for different from different materials, so I'm a little bit curious how those are. Do you use two different printer head that are embedded on the robot arm to realize the fabrication?
Yeah.
How are those how
so actually you can see some of the design. So this is not that one. So if you're looking at the continuous carbon fiber printing, so we have 3 printer head all together, working together. One is for the supporting structures, one's for the matrix material, the other for continuous carbon fiber. So during the printing, we're able to switch from one to the other. So this is the hardware design, but the real hard part of that is actually for continuous carbon fiber, because basically continuous carbon fiber naturally are not compatible with other materials. So basically they are not really binded together with a matrix material. So they allow certain level of sliding inside of it. So when you really 3D print continuous carbon fiber, you need to have more advanced heat treatments and thermal control, and also the certain level of pressure which are applied on the surface to really, simply saying you are trying to ironing those continuous carbon fiber inside into the thermoplastic polymers. But those force actually cause a lot of problems. So think about you have a 3D printed structure which is not completely stable yet. You apply certain force on top of that, it generally collapse in the middle. So all the way, if you observe carefully, you find that all the 3D print of the curved layer-based 3D printing, you go for the later layers, they always generate a lot of uncertainty. This is because during the printing process, all those collapse accumulated all the way to the end. And of course, that's the reason we need to embed in force sensors, camera systems to close the loop of control. So it turns out you're able to have a better quality control about 3D printing process. Okay, I hope I answer your question.
Yeah, thank you. Also, I think that inspires because continuous carbon fiber provides such support. I think when we were discussing about sportswear, some of the current shoe design, they need such carbon fiber materials inside. Yeah. But the manufacturing has been a problem, with the shoe insole foams. I think that could potentially be applied in biomedical design problems. Yeah, thank you.
Okay, thank you.
Oh, thank you for the nice talk. I'm really interested in the complex patterning of carbon fibers, especially I think of, if you envision, coiling a cable, right? One thing that I've experienced, I'm sure you've all experienced, is the twist embodied in that leads to the rotational stresses. And so in your system here, I feel like that would either be, really amplified, right, by having a lot more complicated curvature, right, or perhaps compensated for if it's designed for. So I'm curious if you've seen any consequences of kind of embodied rotational twists inside the fibers.
Thanks for a very nice question. I should point out the most challenging part of that. And so at this moment, we have not really optimized or reduced the twist. And well, one of the, I guess come from me. Okay. One of the main reasons is like we're actually using a thin filament instead of a wide filament. So one of the reasons like wide filament is actually like automatic fiber placement machine, which it causes a lot of problems because it's roll based. So when you have a lot of twist, that makes many of those difference. When we're moving from those like tape, like ribbon continuous carbon fiber into the thin one, it's like actually we're using Markforged filament, okay, which is continuous carbon fiber one. And then we find like the only thing we need to control for them is about their sharp angle, okay? So we are controlled by control the curvature on the curve. Okay, some of the paper I don't cover it here. It's because as long as you're able to control the curvatures on the curve, you're able to control the twist. You're able to control the sharp turn. Okay, so potentially we're able to do that. Actually, in the lab we are already able to do that, but the paper is not published yet. I think that's a very good point that we need to control that. The other thing we need to control is about the curvature of the layer. Okay, so if you have, it's like, simply say you have minimum and maximum curvature, and then if you minimum and maximum curvature go for extreme case, so you need to also generate the hard twist of those printer head during the printing process. So potentially we need to control curvature on the surface layer and also on the toolpath. That's for sure. And at this work, we are mainly focused more on those mechanical strengths. At this moment, we have not really integrated everything into it. So our current plan is like, first of all, integrate design into it, and then we're able to further extend it, have more manufacturing constraints able to integrate into that. Okay, I hope I answered your question.
Yes, thanks.
Yes, please.
Thank you for the very interesting talk. I have a question. If you take a simple 3D printer, you have a very simple kind of planar motion, and you have simple, very precise motors that do very simple motion, and they allow you to keep very high precision. Here you introduce rotations, and you have two sides that are moving, and you have large motors that's moving the entire thing. Each such coupling introduces errors.
Right.
So my question is there a way to quantify these, and is there a way to kind of compensate for these errors that would be kind of unavoidable to some extent?
Analytically, I think it's like the printing accuracy actually about 10 times, the error is 10 times of those position error or repeatability error of the robotic arm. So the quality of 3D printing cannot be enhanced a lot without compensation, you're right. So consider compensation, we're taking like a two direction. One, of course, using the camera system, that gives you a better control about position. And the other thing, we are trying to control the density of material accumulation. Is like we're trying to using force sensor to really control the density of those material which you should deposit on top of the existing surface. So we have a very promising results. It's like with a certain level of like force control, to include in the loop of a printing process, we're able to enhance the density pretty much. Like with the enhanced density, we're able to enhance the like mechanical strengths about 30 to 40%. I think that's a good improvement in my opinion. Yeah, so yes, definitely you are right. The position and also the deposition need to include multiple sensors into loop. But one of the challenges is like the things already printed inside is really hard to kind of monitoring. So it's basically that's why we need to using the force to sense it indirectly. But ideally, if you have the imaging system which can tell you the porosity inside, that allows you to have much better control about quality. Okay. Thank you.
Sorry, you mentioned that you're measuring the force as a mechanism of feedback. Which force?
The compression force at the printer head.
So the force kind of the reaction force on the printer head?
Yeah.
Interesting.
Right. Yeah. So I think that's, how we control it, I can tell a little bit, because when you feel like the force is not big enough, so basically the idea is like we slow down the motion. So basically, a local region, like you have more material accumulated there. That gives a total difference of the printing quality. Okay. The other thing is like you may have the printer jam in the earlier layer. Okay. So this gives you a better way to really compensate and fix those errors in the earlier layer. So if you feel like the current layer you don't have enough pressure, and then so it turns out you stay there longer, so you accumulate more material in those local region. That gives you totally different mechanical strengths.
Any other questions?
Edward.
Yeah, maybe it's related, but like, I guess, do you have issues with sort of varying layer width?
Yeah.
Like if you take like a scalar field and like the iso level sets will be at different like widths. So does this like, you deposit more, until it reaches the height, or like, I'd just be curious for comment.
Yeah, I know you're going to ask this question, to be honest. Okay, so, right, that's definitely yes. I think we need to control it within certain range, but I don't think this is the final solution. To be honest, the final solution will be something like what we discussed. It's about this. Okay. The thing about if we're able to apply the spinning foam onto the surface layer, so potentially we're able to do that, right? So current solution is like we generate non-uniform layer thickness. So with that, we're using adaptive slicing, so like introduce more layers and even more partial layers, trying to potentially solve that. But that is more like the post process. And then we are looking for the opportunity to really generate a direct solutions, like to allow certain partial layer to be represented by the scalar field. And then I believe that is the final solution we're able to cover this challenging. Yeah.
Cool. Yeah. Love to talk about that. Yeah.
Yeah, that's a fun chance to talk more. Okay?
Yeah.
So I think one of my PhD students working on that right now. We are open to collaboration on this. Yeah.
Nice. Maybe just to follow on to in that same line here, when you generate the stripe pattern, how do you turn it into a continuous path? I guess because usually when I think of the stripe patterns, I think of it as like, here's the birth of a stripe.
Yeah, that's
particular singularity.
That's broken. And
is
then,
it so it's an endpoint? It's not like a okay.
Yeah, right. So I think it can. I'm not sure whether these pictures are dense enough so you can see the broken here. So I know like Kin and Chrome have a much smart solution, but when we discuss with like industry collaborators, they just feel like the locally heuristic-based connection will be good enough to use. So we're just simply using that to connecting them together, right? But for those strip pattern work, they have much better, more sophisticated kind of solution to deal with that. But our industry collaborators told us like they actually don't care about this. So it's like no matter how you wind in the back, all those connection continuous carbon fiber does not contribute to any of those mechanical property or whatever things. So they just don't care. As long as it's continuous, they're fine. Okay, so, yeah.
Okay, I think maybe I'll ask offline. I think I'm still a little confused, but.
Yeah.
Right, well, we're at time, so I'll cut the questions off there, but thank you so much for being here, Charlie. It's really wonderful to learn more about your work, so thank you so much.